All right, so what we have here is our first video podcast. And what we're going to do is you should have this sheet in front of you. And I want you to be listening to me talk and adding some notes about things that I talk about. And I'm going to be writing those things on this piece of paper as well. But this allows you to work on your own, allows me to touch base with each kid, and also run lab in class. So there are lots of things going on. I hope you feel busy. I hope there's a lot going on and that you feel that there are lots of resources, because there most certainly are. So what we're going to do is go ahead and get started here. So enzymes and macromolecules. So let me just point out that this is going to be review, and based on the quizzes, this is much needed. So we're going to make sure that we understand this material and that you understand it pretty well, better than you did for the last quiz. So let's look at this. Enzymes are a special group of something that are used to break down large molecules into smaller ones. Well, let's look at this word. Break down large molecules into smaller ones. So you should know that this is actually digestion, right? So digesting is just breaking things down, but this is chemical digestion. And sometimes that reaction is going to have, it sometimes has a special name. So I'm going to throw a new vocab word at you. And those are quotation marks right before that H. So it's Hydrolysis. Hydrolysis. Hydro refers to water, H2O, and lysis means to break. So by throwing lots of water molecules at these large molecules and using these enzymes, we break these large molecules into small ones. Oh, sorry, that was my other computer booting up. Apologize about that. So these large molecules, another word that we know is polymer. These polymers break down into monomers, right? Mono meaning one, okay? So we're going to talk about the monomers and the polymers and the monomers of each of these categories, proteins, carbs, and lipids, as a review. But the enzymes are a special group of proteins, which might be weird. These are a special group of proteins that break down other types of molecules. So enzymes are a special type of protein that can break down other proteins, or it's a special group of proteins that break down carbs, or a special group of proteins that break down lipids. And so we're going to talk through that today. So here's my diagram over here. I'm going to use a different color pen. I'm going to use let's go with green. No, I apologize. I'm going to use red. So we've got our enzyme and we've got our substrate. And so remember that we call this model the lock and key model. So lock and key. So if you think about this, there's one shape of a key that works on a lock. And when we turn that key in the lock, it changes the lock, but the key doesn't change. And so that's really important to think about with our enzyme and our substrate. Our key is the enzyme. This is our key. And it fits into the substrate. And when we turn this key, it changes the substrate so much so that what ends up happening, let's see if we can animate this a little bit, so much so that the lock actually becomes unlocked, right? And so when it becomes unlocked, the lock has changed shape. But has the key changed shape? No. And so that's really essential for your understanding, is that this enzyme can be reused. It can be reused over and over and over again. Okay? As long as this key doesn't change shape. But the moment this key changes shape, it's no longer going to fit into the substrate or to the lock and change the shape of the substrate. So that's key to think about. So let's talk about how these enzymes work on different substrates. So if we had proteins as our substrate, or carbs as our substrate, or lipids as our substrate, that enzyme is going to do different things to that substrate. So again, I'm going to use a different color. So proteins. So protein is itself the polymer, but sometimes it can be referred to as a polypeptide. Okay? And that's the polymer. Polymer means many blocks, or many building blocks, right? I'm just going to write blocks, but you should write many building blocks. And the monomers that these proteins get broken down to are called amino acids. And the enzyme that works on this substrate is called, we're going to call it a protease. And notice the ASE ending. Anything with an ASE ending is an enzyme. The product are amino acids. In our digestive system, these are so small they can be absorbed by the villi of the small intestine. So those are the proteins. And I guess I'm going to add one other little note here. Let me see if I can find my cursor. Keep losing it. Okay, there it is. So proteins have carbon, hydrogen, oxygen, and nitrogen in them. And nitrogen is key. Good way to remember that is that there's an N in proteins. Okay, but when we talk about the other macromolecules, we've got our carbohydrates, and the polymer is called a polysaccharide, and the monomer is called a monosaccharide, or the dimer is called a disaccharide. Saccharide means sugar. Mono means one, di means two, poly means many. And the enzyme that works on these, well, we have to be a little bit more specific because there are lots of different enzymes. But if we had, let's say we had starch, also known as amylase, amylose, then the enzyme on that would be called amylase. And again, we have the ASE ending. And the product would be maltose. OSE tells us that it's a carbohydrate. And the carbo part refers to a carbon, and the hydrate part refers to water, which has hydrogens and oxygens. So all that carbs have in them are carbons, hydrogens, and oxygens. Alright, so we have lots of examples, and you should review those. But what we have now, the last group, are lipids. And the polymer can be lots of different things, but the one we've spent most time talking about are fat and phospholipids. And the monomer or dimer are fatty acids and glycerol. We just have different numbers of fatty acids. The enzyme that works on this substrate, these are lipids. The name of the enzyme is called lipase. And again, with the ASE ending, and the product are the monomers. So again, we've got fatty acids and glycerol. Okay? And in lipids, we've got carbon, hydrogen, oxygen, and the phospholipids happen to have a phosphate or a P in them. Okay? So that's the first top part of our chart, but I'm going to go ahead and scroll down. I want you to look at these diagrams. I'm going to go ahead and pull my screen down a little bit. And so what we're looking at here is different rates of reactions. And so if we look over here, we've got rate on our y-axis and we've got temperature. So what we see here is the temperature increases, the rate of the reaction increases up to a certain point. That point is, this point right here is the optimal temperature for that enzyme. And then what happens is that the enzyme comes crashing down, so there's a low reaction rate. And what's really happening is this enzyme right here, and this substrate are no longer able to fit together, because when it's heated, what ends up happening is that this section right here, which is called the active site, has changed shape. And therefore we say that it is denatured. Okay? It has changed shape, which means if this shape is different, then the substrate doesn't fit in there anymore, and therefore the reaction doesn't happen quickly, and the rate of reaction comes crashing down. Same happens over here with these enzymes, and I'm going to scroll down just a little bit more so you can see down here is pH, right? So pH. So anything to the left of 7 is acidic, anything to the right of 7 or greater than 7 is basic. So what we see here is pepsin has an optimal pH here around 2 or between 2 and 3. Salivary amylase in your saliva has a pH just about 7. And arginase, which is a different enzyme that we didn't learn about, has a pH of about 10 or 11. And so each of these enzymes have different optimal pHs. And what happens beyond these optimal points or best points, again, we've got denaturation happening. Okay? And then what we've got here is another picture that's similar to this one, except this diagram over here on the left, the one I put a star next to, has 3 different enzymes with 3 different optimal pHs. The one over here on the right is one enzyme with an optimal pH. There are no values on here because it varies from enzyme to enzyme. So think about where in the digestive system this is happening. This pepsin is a type of protease. A protease works on proteins. The protease is made in the stomach, which has an acidic pH. Salivary amylase is in your mouth, and that's about a pH of 7. So I want you to think about this. What might happen to the enzyme activity of salivary amylase when you drink soda or coffee or something else that is acidic, that pushes the pH way down here? What does that do to the enzyme and the reaction rate? Okay? And how does one recover from that? I think those are all interesting questions. The last one you may or may not know the answer to, but these are questions that you should be ready to answer if Ms. Hartnett and I come by and quiz you before you go to lab. Okay? I'm going to stop there. I see I'm at 12 minutes and almost 12 and a half minutes.